All right, this is not the latest because I just updated it. Let's see if it will update. People I don't see here. I don't see Hannah. Ryan just arrived, and I don't see DJ.
You do see me.
You what? Okay. I've been working so hard on focusing on problems that I think I've actually done less problems in class. So all I am going to do today is work out some problems. And I'm going to start by working out this one because Mira suggested that maybe I've only talked about this in the astronomy class and not in general physics. Have I talked about gravitational force in its general form here? No? Okay. So let's quickly do that. Isaac Newton, during the year when there was the Black Plague and no school, a little more than a year, he was at home working in physics, came up with his 3 laws of motion that we've discussed. We have discussed his 3 laws of motion. I'm 100% certain of that. And he developed physics calculus so he could work with those. And he developed the law of universal gravitation, a law to explain how gravity force can act at a distance. So that law says that the force of gravity is equal to a constant g, which is what, 6.67 times 10 to the minus 11 newtons times meters squared per kilogram squared. It's just a constant that's experimentally determined, times the mass of object 1 times the mass of object 2 over the separation between the centers of masses of the 2 objects. So that's the equation for the force of gravity. That one always works. The one that we've been using so far, force of gravity is equal to mg, works if you're on the surface of the Earth. On the surface of the Earth, mass of object 1 is the mass of the Earth. The radius between the center of your mass and the center of the Earth is the radius of the Earth. And if you jump up a foot, that's an immaterial difference in the radius. So we just treat that g as a constant. So when we use g is capital G times the mass of the Earth. Okay, for some reason, it stopped writing. Okay, it just crashed. Excellent. By the way, I'm doing this in OneNote today, so if you have, you can follow along and see everything I'm writing on OneNote.
So if you had a tunnel to the center of the Earth, the 9.8 would increase.
Actually, the way this gravitational worked, Newton also during the same time did what's called Newton's synthesis, where he used his calculus to calculate what the gravity would be if you are inside or outside of a spherically symmetric shell. And it turns out that if you're outside of a spherically symmetric shell, then it's as if all of the mass is at the center. But if you're inside a spherically symmetric shell, that is, if there's mass all around you in a spherical shell, no matter where you are inside, the forces are going to add to 0. The result of that means that if you were to be able to drill this mythical tunnel through the Earth, such as in the remake Total Recall, as you go toward the center, the amount of mass that's at a bigger radius than you is getting bigger. The amount that's at a smaller radius is dropping. And it's only the amount that's between you and the center that matters. And so the acceleration of gravity would actually decrease as you go toward the center of the Earth. And if you go through the calculations, it turns out that I'm pretty sure it decreases in a linear fashion. So the acceleration of gravity would decrease linearly until it's 0 at the center. So if you watch the remake of Total Recall, which is not nearly as fun as Total Recall, both of them are kind of bad physics, Total Recall, they turn on the oxygen generator, and within 10 or 15 seconds, the planet has a high enough air pressure to live and breathe. That's Mars. And in the remake, they go through the center of the Earth on this little shuttle. And as they go through the center, all the way down to the bottom, they're just being pressed in their seats like normal. And then at the bottom, boom, it changes from one side to the other. That's not the way it would happen, which is what your question was essentially asking.
I guess at the center, you have equal amount of mass on
Yeah, so it'd be 0 at the center. And then there's the problem of we have a molten core. It's so hot that everything's molten. You go even further, the pressure's so high that even though it's so hot, it compresses it to a solid core in the center. So drilling a hole through that is improbable. We hate to say impossible, but yeah, it's not possible with anything known to man.
Another planet or a star.
Anyway, so the G that we've learned is 9.8 meters per second squared. Is just that relationship. Now you notice that it has to do with the radius. So the new house that we purchased near Hartzell has an elevation of 9,400 feet. That's a fair amount higher than what it is here. And so the acceleration of gravity there is going to be, you divide by radius squared, slightly less. So that means if I step on the scale there, I will weigh less. By some immeasurable amount, probably, but it's going to be less. So G isn't a constant. In fact, G varies. The Earth is not spherical in shape. The Earth is fattest at its waist, just like most of us, or many of us. And so the acceleration of gravity is actually a little bit smaller at the equator and bigger at the poles because it's a little bit, well, it's because it's spinning that you have it elongated. Also, you have an effective G because of the force necessary to make you stay on the surface of the Earth. If you step on a scale, what the scale is going to read is the force of gravity minus the centripetal force necessary to keep you on the Earth. So you have that as well. Okay, all of that said and done, let's get to the problem. This says if you have a planet, so here's my planet, M sub P, and you have a moon, so here's my moon, M sub M, and they are separated by D equals 31 times 10 to the 5th kilometers. And then it asks, I should put M sub P was 14.2 times 10 to the 26 kilograms, and M sub moon is equal to 5 times 10 to the 23rd kilograms. I know they didn't use a subscript for one and they only used it for the other. I hate to only use one subscript here. They use a capital and lower. You wouldn't know the difference in my capital and lower, so have to use the subscripts. Then finally, at what distance x on the line that is separating the two do you have a net force of 0? So now we're to things that you can do. By the way, if it's x from the planet to that point, what's the distance from the moon to that point? Not the same. It's d between the two. It's x to 1. So what is it? D minus x, yeah. So if it says the net force is 0, what does that mean? Net. What do we usually write?
The pull of one planet and the other pull of the other planet cancel out. So it'd be like x minus d minus x equals 0.
Okay, so first I'm writing just a mathematical equation. Sum of the forces, that's what net force means. Sum of the forces equals 0. I need to make a free body diagram. I need to draw the forces acting on the object. In this case, it's really simple, but we want to get practice at doing it when it's simple because, sometimes it's not going to be simple. And so the force of gravity, another thing that I must say is gravity is always attractive. So there's a gravitational force that's attracting every object that has mass to every other object that has mass. So Leslie has mass. Leslie's phone has mass. There's a gravitational force attracting Leslie's phone to Leslie. It's not very strong because G was 6.67 times 10 to the minus 11 newtons per meter squared. If you take the mass of Leslie, it might be, let's just say 50 kilograms. The mass of her phone, let's say it's 0.5 kilograms. I'm sure it's less than that. So 0.5 times 50 is 25 times 6.67 times 10 to the minus 11. Just between friends, let's call that 1 times 10 to the minus 10. So 1 times 10 to the minus 10 times 25 is 2.5 times 10 to the minus 9. Then you divide by a meter squared, and you still have 2.5 times 10 to the minus 9 newtons. 2.5 nanonewtons. It's not going to make a difference. But in this case, it will. So I need to draw my force vectors. So I have two objects. So if I have something here, it's going to have one force that's attracting to the moon, and one here that's attracting to the planet. If the sum of the forces is 0, then I'm going to have, just looking at my arrows, I need to decide what direction to call positive. What direction should I call positive? Somebody blurt out a direction. North works, except for in this problem, I need something more specific like left or right. Right, okay? So I'm going to call to the right positive. And so when I look at my picture, I draw the Freebody diagram as I put the forces on my object, so I can look and say, aha, the moon is in the same direction that's positive. And so that means when I do the sum of the forces, I'm going to have the force of the moon as positive. The planet is in the opposite direction. It's in the negative direction. So that means I'm going to have minus force of the planet. Or then, writing that more simply, the force of the moon has to equal the force of the planet. Well, since for both of them the force of gravity is g mass 1 mass 2 over radius squared, I can now substitute g times the mass of the moon times the mass of whatever my object is that I'm looking at, because we never defined it. We weren't given a mass force. I just call it m sub o and say, better work out. Divided by the distance between the moon and my object squared, so that was d minus x, is equal to g times the mass of the planet times the mass of my object over the distance between the planet and my object, which was x squared. Now, I did something really silly 10 minutes ago when I was solving this with Mira. I went ahead and expanded d minus x quantity squared. That's silly because the smart thing to do is to square root everything. If I square root everything, well, first I can do some canceling. What can I cancel? The g's. There's another thing I can cancel. The masses of the object. Good. Remember I said we don't know them, so I just put m sub o and trust it's going to work out. It did. If it didn't work out, then you'd say, bad problem. Can't find a solution. Square root this, and I end up with an equation that says cross multiply and factor I'm just going to divide everything right now by square root of MP. And I have x times square root of mm over MP equals d minus x. Rearrange. Or finally, and there we have the position where the net force is 0. And now I know some people spent time and put in random guesses, and lost a lot of points because anytime you answer the wrong on a multiple choice, you lose 1 divided by how many answers there were minus 1, which is a lot. Any questions about how we solved that problem? If you have questions, you do need to ask them. Yes?
How do you know what to set what equal to? Like, I guess there's I could usually pick out one equation, but then there's another thing that'll equal it, and that's where I get confused. I'm like, how do I know which one to choose equation-wise? Because you set 2 equations equal to each other, like.
The way I knew was because it said the only condition I had was the net force in the object is 0. So that was the equation I used. The net force is 0. And so net force is 0 is sum of the forces equals 0 because net force means add up all the forces. And so then I made my free body diagram because I knew I was looking for the net force. Look at all the forces in my free body diagram, put them into that equation, and then it's math after that.
Yeah, but I'm saying like on the bottom, you ended up with like the G.
Oh, you're talking about just the math work?
How do you know that you just set them equal to each other like that?
Well, it came from what I just said. Sum of the forces is 0. So there is sum of the forces is 0. I looked at my free body diagram and I put them in. And so then I rearranged this equation to get to this equation. And then I substituted what force moon was and what force planet was. Right, so there was no guesswork once I had identified net force as 0. I just plugged in and chugged.
Yeah, but I think what I'm confused on is that you knew that it was going to be over D minus X squared and like, was there like an equation?
Because yes, that's this equation right here.
Yeah, those. So you set them equal to each other?
Because the net force was 0.
Okay. All right.
Okay, Lydia.
Yeah, when you were deriving everything and figuring out what you were doing over there, how did you get the 1 plus? How did you find that 1 plus there?
Okay, I did do one step quickly. I added X to both sides. So I had X times square root of mass of the moon over mass P plus X equals D. And then I factored out the X. So to keep things in the same order, that's what you get if I kept them in the same order. So the things in red are what I didn't show for the intermediate steps. Any other questions? I think I did show all the intermediate steps beyond that. All right, let's do a second problem. The pulley system shown below has mass 1 is 100 kilograms and mass 2 is equal to 400 kilograms. Notice I put periods after the 100 and after the 400 so you know those have 3 significant digits in them. What is the acceleration of mass 2 and what is the tension? Now let's start this problem off by guessing. Right? Guesses can clearly be wrong. What do you think is going to happen if the system is released?
M1's going to go up.
Yeah.
Okay? James says M1 is going to go up and M2 is going to go down. So, and that's also the correct answer, but like I said, guessing can be wrong. If he was wrong, I wouldn't have felt bad or anything. Okay, James would have. So now we want to go ahead and figure out how is this going to work. And before I start, I want to look at some constraints. This is in physics, we make a lot of assumptions. We make the assumption of ideal pulley. There are 2 pulleys here labeled P1 and P2. An ideal pulley means the mass of the pulley is equal to 0. So that pulley 2 is going to move up and down with mass 2. But our ideal pulley has no mass, so its mass doesn't affect my problem. And second of all, they have no friction for spinning.
Do you just assume that in any pulley problem that there's no friction?
Unless told otherwise, that's correct. We assume these ideal conditions. So no friction for spinning, it just spins freely. If that's the case, then the tension is the same everywhere in the problem, provided that we have an ideal string. So ideal string. The mass of the string equals 0. Sure, I have lots of string here. You know what the mass of this is not? 0. But it's an approximation we make. Is it reasonable? Usually it is, because the mass of the string is negligible compared to the mass of the stuff around it. Question?
So will there be problems like if the mass is not 0, would we add that to?
If the mass is not 0, you could have that in the calculus problems because we can integrate. And so we can get the mass, if we have the mass per unit length, we can calculate. But in the general physics class, no. They're just simply not going to experience that at all. You're probably not going to experience it in the calculus class, but you could. Okay, second one is no stretching. Which reminds me, homework problem number 4 is worth nothing. Homework problem number 4, the one with stress and strain, is not counting toward your homework grade. It's still there, so you can work with it, but I didn't lecture on stress and strain, and I'm just not going to hold you accountable to doing homework on that. So it's there for you to enjoy, but not for you to be graded on. Okay, coming back to this. The string is ideal, which means it doesn't stretch. Which, this here doesn't stretch, right? Well, that's because it breaks. Most strings will stretch. So if we have ideal string and ideal pulleys, then if we go with what James said, if mass 2 goes down, mass 1 is going to go up because the string is staying constant in length. How much is another question that just needs to be reasoned out. Let us suppose that M2 moves up a distance x. How much string has been removed from each side of those verticals that go down to pulley 2? If the pulley goes up a distance x, how much less string is on the left side of pulley 2? X. How much less string is on the right side of pulley 2? X. Somebody's mouthing the words, and I'm just saying them out loud so everybody can hear. So if there's X missing on both sides, what's the total amount missing there from pulley 2? 2X. So how much is mass 1 going to move down if mass 2 goes up a distance X? 2X. So that means if change in height 1 equals X, then change in height 2 is equal to 2X. But there's another thing there. If change in height 1 was up, what direction was the change in height for 2? Negative. So we have a relationship there. Wow, I erased the wrong thing. That says what happens for the pulley number. Oh, I put them in the wrong order. I put them in the wrong order because I thought the left one is 1 here. And this is, of course, vital to make sure you have them correct. If mass 2 moves up a distance x, the mass 1 moves down a distance 2x. And so we have the signs reversed because one's up and one's down. We have the 2, and the easy way to get this once you've gone through it is there are 2 strings coming off of here. 1 string here. So it has to be a 2-to-1 ratio. And there are lots of different ways to string things up where you can get different ratios. So when we use these, if that's the change in position, then if I do the velocity being changed in position over time, we're going to have that same minus 2-to-1 relationship. And if we do the acceleration, the change in velocity with time, we're again going to have that minus 2-to-1 relationship. So we are going to have from this the relationship that acceleration of object 1 is equal to minus 2 acceleration of object 2. Minus because the accelerations are going to be in opposite directions. The 2 because of the 2 strings on object 2 versus 1 on object 1. So that's the setup. Now we're ready to do the problem. So look at the problem. We're looking for the acceleration. There's nothing in this that tells you how to solve it. So you have to now think physics. What ideas are going to apply here? So what do you think? What ideas are going to apply here?
Gravity.
Okay, I am going to have to use the acceleration of gravity here because gravitational force is acting on both of those objects. So gravity. What else?
We'll be talking about tension at all.
We'll be talking about tension. Yes. One more important idea. Not velocity. It's the important idea that allows us to solve the problem. To narrow it down a little. What?
No.
What is the way we solve most force problems?
Freebody diagram.
Okay, Freebody diagram is there for the specific reason of how we're going to solve it.
One-dimensional motions.
Some forces.
In this case, it's one-dimensional. There, Leslie got it. Newton's second law. This is one-dimensional. The next problem won't be one-dimensional. Newton's second law is how we solve most of our problems. So we're going to apply Newton's second law. And you come to the test, and it's not going to say, apply Newton's second law to find this. It's going to be worded like this, where you have to do your physics. Your physics is thinking, what fits in here? What's going to work? And so I need to apply Newton's second law. Now, Newton's second law says the sum of the forces on an object is equal to the mass times the acceleration of that object. Mass of the object times acceleration of the object. In this problem, you might say, hey, wait, I have 2 objects. I have mass 1 and mass 2. Do you agree? So would I. So you know what I have to do? I have to make a Freebody diagram for each object separately and then make one Newton's second law application to one object and one to the other. I can't just look at this and say, well, I have mass 1 has force of mass 1 times g, mass 2 has force of mass 2 times g due to gravity. So my net force, I can't just say my net force is the sum of those two and divide it by the mass of mass 1 plus mass 2. It's not going to work because that's forgetting that there are other things going on like the unknown forces of the roof and whatnot. By the way, that red line with the slashes, that just means a stable object is not going to move. So the strings are tied to that so they don't move. So I need to make Freebody diagrams for object 1 and object 2. So I'll first do object 1 just because 1 comes before 2. Here's my object. What forces are acting on it? Force of gravity. And I know this is the most ridiculous question, but I do want an answer. What direction is the force of gravity? Down. Thank you. So I have a downward force gravity 1 equals m1g. What other force is acting on object 1?
Tension going up.
Tension. And remember, and notice he said going up because the force of tension is always in the direction that the string is leaving the object. So we have force of tension equals tension that's going up. This was object 1. I meant to write 1, but I got carried away and did other stuff. So I have my Freebody diagram. What was the purpose of the Freebody diagram? to apply Newton's second law. That was the whole purpose of making this free body diagram. Now, before I apply Newton's second law, there's one more really important thing I have to define. What direction is positive? Now, I'm not going to let you choose. I am going to choose that up is my positive y direction. So I apply Newton's second law. Sum of the forces in the y direction is equal to mass times acceleration, and I'm going to call this 1 because it's object 1. So I look at my picture to replace the left-hand side. What do I get when I replace the left-hand side of Newton's second law? I have, how many forces do I have in my free body diagram? 2. So that means I'm going to have 2 items when I replace the left-hand side. I always do positive first. Which of those forces is in my positive direction? Tension. So I'm going to have tension, and then M1G is in the negative direction. I just put M there. That was silly. Sum of the forces on an object is mass of the object times acceleration of the object. So I really should have had a mass subscript 1 there. So there is one equation. I can't solve it yet because I know neither the tension nor the acceleration. But it's an equation, a correct equation that I'm going to use for my solution. So now I go to object 2. Object 2 for my free body diagram. Note that I have 2 strings going vertically. So that means I'm going to have two tensions pulling up. And then, of course, I still have gravity. M2G going down. Why did I make a free body diagram? I'm asking the questions over and over to make sure it's very clear. So you do homework, you do a test problem, there's no question. I did it so I can apply Newton's second law. So sum of the forces in the y direction is equal to mass 2 times A2. Right? Because now I'm looking at object 2, that's why it has the 2's. Looking at my picture, what do I get when I apply Newton's second law? Okay, 3 forces. So what do I get writing them in? Perfect. Now, she said force tension 1, force tension 2, which is also perfect. I wrote tension and tension because force tension 1 has a value of tension, and force tension 2 has a value of tension. Notice, because we have ideal pulleys and ideal strings, the tension has a magnitude of tension everywhere. That's why we use tension for it.
So you can just do like 2T.
Right. Because force tension 1 has a magnitude of T and force tension 2 has a magnitude of T.
So it's 2T because they have the same magnitude? Is that right? Or?
Yes, because I have 2 tensions, each with magnitude T.
Same magnitude?
Yes, they're the same magnitude. So there is another perfectly correct equation. So now I have 2 perfectly correct equations. One has tension and acceleration. 1 is unknown. 1 has tension and acceleration. 2 is an unknown. I still can't solve it because combining the 2 equations, I have 3 unknowns. But we already specified the relationship between acceleration 1 and acceleration 2. So the problem asked us to find what is the acceleration of mass 2. So that means I want to solve for acceleration 2, so I'm going to substitute for acceleration 1 so that I eliminate acceleration 1. So if I substitute this into here, I will get that for my equation, or more simply, that. Now combining these two equations, I can eliminate tension and solve for acceleration. Random question, let's see. Somebody who hasn't answered anything today. Clayton, how would you go about eliminating tension? What? Do a. Okay, somebody want to help? How would you eliminate tension from these equations? Okay, Sarah says solve for t. So choose one of the equations, solve for t, and then plug that into the other. That's the standard method. It works perfectly. I'm going to do a different method just so you can see that there's more than one way to do this. I'm going to take these two equations and stack them. And then I'm going to take the lower equation, multiply it by 2, and subtract the two equations. It's fundamentally the same thing as what Sarah said, but it drops out quicker. So if I do that, I'm going to have 2t minus 2t, so I'm going to have 0 in that column. Then I'll have minus m2g minus a minus, so plus 2m1g. And then on the other side of the equal sign, I'm going to have m2a2 minus 2 times minus 2 makes plus 4, m1a2. Now let's factor things. Divide everything by whatever A2 is multiplied by. And then let's put in values. On top, you have 200 kilograms minus 400 kilograms minus 200 kilograms. On bottom, you have 400 kilograms plus 400 kilograms, 800 kilograms. Minus 200 over 800 is minus a quarter. So the acceleration is minus a quarter g. Now that tells us that James was correct, that it's going to accelerate upward. And now we know the magnitude, 1/4 g upward. I say upward here. That's downward. Whoops. Downward, 1/4 g downward. 1 goes upward, 2 goes downward. That is what James said. I just said it backward here. So the minus side is downward because, we go back to our picture, up was positive. So now we have the acceleration. How do I find the tension now? Well, now I'm going to do what Sarah had suggested. I'm going to go back to one of my two equations, whichever one I find easier. You know, there's really fundamentally no difference in the one you choose at this point, and substitute the acceleration in. So I'm going to put into the, that one has a 2t, so I'm going to put into the one with a 1t, just so I don't have to divide by 2. Tension is equal to m1g minus 2m1a2 equals m1g minus 2 m1 times minus g over 4. Minus times minus is plus, of course. So it's going to be m1g times 1.5. So I had 100 kilograms times 9.80 meters per second squared times 1.5. And so that's 980 plus 490, 14. I don't know. I feel stupid. I thought my brain's not working. 1470. Yeah, is that what you said? Yeah. Now, if you look at that 1470, you're like, oh, wait. We have 1470 newtons pulling up on mass 1. How much is pulling down on mass 1? Mass 1 being the 100 kilogram block that's hanging by itself. 1470 up. Down is going to be 980. So we have a net force of 490 newtons up. And so the acceleration on that is going to be that net force divided by mass 1. And then I could go over to the other one and calculate similar. Hopefully I did all that math right in my head. So that's a simple one-dimensional Newton-second law problem. My next problem here is involving a spring. Now, I was going to do this problem, but I'm also going to change up lab. Remember I said I've been focusing so much on problems, I've been having students work problems, but that takes more time with the problems, and I haven't had as much time to solve problems myself. So for lab tomorrow, you don't have to do the pre-lab quiz, because for lab tomorrow, I am going to be solving problems and giving you problems to solve, you and your partner in your lab group. So your entire write-up will be, number 1 is writing down my solution to a problem, and then number 2, writing in the same formulas of your solution to a different problem. So you don't have any pre-lab write-up, you don't have to do the pre-lab quiz. And we'll just be doing problems for lab tomorrow as well. Because problems, you've got to do problems in physics if you're going to be able to solve them. Yeah, Emily?
Is it over section like chapter 5 and 6? Or
well, I believe we started with forces in 4, and then 5 and 6 are continuing with forces. So yeah, we're going to have force problems which covers that whole range. And yeah, you can look at the lecture here and see the next couple problems I'm going to solve, because there's a problem 2, problem 3, problem 4 here that I'd set up for today just to make sure I'm covered. And so I'm going to be solving those in class or in lab tomorrow. And one of these I'm going to have you do the solution with me, so you have written down your version of my formalism. And then you're going to do another one showing the same formalism. All right. I'm finishing 5 minutes early because I can't get started on a problem. My problems take more than 5 minutes to get started.
can you do like problems from our previous homework? I really struggled with it.
I certainly can. You want me to try doing it right now, or?
No, I mean like for tomorrow, like those styling questions. There was any questions.
Sure. Just tell me the questions. Come and say, how about this one?
About last one. You just want me to come with questions about the previous homework tomorrow?